Hello everyone, my name is Zeif and I'm going to talk about the balanced crown decomposition, which is a structural theorem for graphs. This is a joint work with Katrin, Casel, Tobias, Friedrich, Davis, Issac, Aikaterini, Niklanovits and me. All of us are in the algorithm engineering group at the Hasso-Plattner Institute. First, let me introduce the term of a crown decomposition. Inspired by a king, we decompose our graph into a crown, head and body part. As it is the case by a king, the head separates the crown from the body. Usually there are structural properties given by the head and crown. What is new and what we did is that we also give structural properties of the body. Next we go through the history of crown decompositions, where we finally end up by the balanced crown decomposition. First, let us think about by crown decomposition that this is a tool for reduction rules. What is a reduction rule? Suppose you have an instance of an optimization problem, you know some reduction rules for it. Afterward, you are allowed to consider a reduced instance without influencing your optimization problem. Let me illustrate this by the famous vertex cover problem. Given is a graph and our goal is to find a minimal vertex subset such that each edge is covered by this vertex subset. What means covering here? For example, this blue vertex covers these three blue edges. The next picture illustrates a vertex cover given in red. You can verify this by picking an arbitrary edge and then you will see that this edge is incident to at least one red vertex. It is a known result that after removing a vertex cover, the remaining vertices forms an independent set. The independent set is the set of vertices such that there is no edge in between. Now let's come back to the reduction rule. It turns out that we can pick this red vertex beforehand to our solution for a vertex cover and are allowed to reduce our graph by these three vertices here. Why this is possible and where the connection to the crown decomposition is comes now. The vertex that we pick in our solution is our head vertex. The vertices that becomes to be isolated after removing the head vertex are our crown vertices. The remaining vertices are our body vertices. The first property of a crown decomposition is that the crown vertices needs to form an independent set. Moreover, we wish to find an injective mapping from the head vertices to the crown vertices such that we have always an edge in between. What is here the idea of the mapping? For example, when we consider the vertex cover problem, we obtain a lower bound for this part of the graph for the vertex cover problem. For example, we found here through this mapping an edge that needs to be covered. Finally, it is provable through the properties of the head vertex, because it separates the crown from the body, that we can pick the head vertex to our solution and allow to reduce our graph by these three vertices here. The idea of the mapping becomes more clear if we have more than one head vertex. Let's say we have three head vertices and we have an injective mapping from the head vertices to the crown vertices such that we have always an edge in between. Because our mapping is injective, we know that the edges that we found in this part of the graph are disjoint. That is, we need at least the number of head vertices for a solution of a vertex cover for this part of the graph here. On the other hand, if we pick the head vertices, then we obtain a feasible solution for this part of the graph because the crown vertices forms an independent set. Finally, it is provable through the separation properties of the head that we can pick the head vertices as part of our solution and are allowed to reduce our graph by the head and crown vertices. And this is now exactly the classical crown decomposition. We decompose our graph into a body, head and crown part where the head separates the crown from the body. We want to have an injective mapping from the head vertices to the crown vertices such that we have an edge in between always. And we want that the crown vertices forms an independent set. The classical crown decomposition finds also some other applications except of the vertex cover problem, but let's go further with the next crown decomposition called Q expansion. And the only difference is now the following. Instead mapping one head vertex to one crown vertex, we want to map one head vertex to Q crown vertices. Here's an example for Q equals to 3. We can see that each head vertex are mapped to exactly 3 crown vertices. What is important here is that the mapping needs to be disjoint. The properties of a Q expansion are analog to a crown decomposition with the only difference which I already explained. The Q expansion finds also some applications, But again, let's go further with the next Crown decomposition called W-weighted expansion. And the first difference that you need to observe by this picture here is that instead having only vertices in the crown part, we also allow to have connected components in the crown part. Let me explain the W-weighted expansion on a precise example where W is equals to 4. We define the size of a subgraph as the number of its vertices. For example, this component here has size 3. What we want to have is that each connected component in the crown has size less than W. Here W is equals to 4, and we can see that the size of each component is at most 3 here. For convenience, we change our mapping. Instead going now from the head vertices to the crown components, we want to go from the crown components to the head vertices. What is here the advantage? We can use the properties of a function to obtain a disjoint mapping. In other words, we want that each connected component of the crown is mapped to exactly one head vertex. Finally, we can use the inverse function to encode the components that we map to a head vertex. For example, we map these 4 components to this head vertex. If we take the inverse function of this head vertex, we obtain these 4 components. What we try to achieve through this mapping here are to find disjoint connected subgraphs such that each of them contains exactly one head vertex here. Moreover, we want that each subgraph has size of at least W. Here this is illustrated in blue. The weighted expansion, also called W-weighted crown decomposition, can be extended to vertex-weighted graphs. Here you need to know that we define the weight of a subgraph as the sum of its vertex weights. We say CHF is a weighted crown decomposition, where C is the crown and H is the head, if the head separates the crown from the rest of the graph, where the rest of the graph is our body. We want that each connected component of the crown weighs less than W. Moreover, if we map a crown component to a head, then we want that this crown component is also connected to this head vertex. This property ensures that we obtain through the head vertex with its inverse function connected subgraphs. Finally, we want that the subgraph, which is defined through the head vertex and its inverse function, weighs at least W. Before coming now to the balanced crown decomposition, let me introduce the W packing problem for a perfect understanding of the balanced crown decomposition. So given is a vertex-weighted graph and the parameter W, and our goal is to find a maximum number of connected disjoint subgraphs such that each of them weighs at least W. Here's an example for 3 subgraphs. All of them are disjoint, each of them are connected, and each of them weighs at least W. For example, this subgraph here weighs W plus 4. Now we are ready for the W balanced crown decomposition. We say CHRNF is a W balanced crown decomposition if CHF is a weighted crown decomposition. So this part of the graph is the weighted crown decomposition. Additionally, we want to have a connected vertex partition of the body such that each part weighs between W and 3 times W minus 3. And our main result is that we provide a balanced crown decomposition in time k to the square times the number of vertices times the number of edges, where k is bounded by a maximum W packing. Finding a balanced crown decomposition is more technical, and unfortunately the time is not enough to explain how we can find it. But let me give you the strengths of the balanced crown decomposition, some improvements that we did in comparing to the previous structures, and also some applications how we can use the balanced crown decomposition. So first of all, we give now a structural characterization of the crown, head and body, what is a full characterization of a graph. You can imagine this as a measure for robustness regarding the connectivity with respect to a parameter W. Moreover, we extend the weighted crown decomposition also for vertex-weighted graphs in polynomial time. Before this was only possible in pseudo-polynomial time. Next, I'd like to point out the ratio factor of 3, which describes the weight of each part of our connected partition of the body. We guarantee that we find the connected partition of the body such that each part weighs between W and 3 times W minus 1, where 3 is the ratio factor here. This ratio factor is crucial for all of our results. For example, all kernelization and approximation results contains this ratio factor of 3. In other words, if you can improve the ratio factor, let's say you guarantee that each part weighs between w and 2 times w minus 1, then you also would improve all of our results. However, it turns out that the ratio factor of 3 is best possible for a balanced crown decomposition, which shows that the ratio factor of 3 is not chosen arbitrarily, rather it is best possible to find a balanced crown decomposition. Next, we will see how we can use the balanced crown decomposition. For example, it is useful for vertex separating or vertex covering problems, for subgraph packing, subgraph partitioning, or subgraph covering problems, for example. These kind of problems have also a lot of practical applications, for example positioning, for example in car sharing, graph separation in case of an epidemic, task allocation, for example robotics, or graph segmentation, for example image processing. The balanced crown decomposition finds also modular applications in form of a divide and conquer algorithm or in parallel processings. Next, we want to design a kernelization algorithm through the balanced crown decomposition. Given is an instance of an optimization problem again, let's say you know some reduction rules for it, you use them and afterwards you allow to consider a reduced instance without influencing your optimization problem. Now you want to know how good your reduction rules are. And the measure how you can do this is to bound the reduced instance by some given instance parameters. And this is now the idea of kernelization here. What is the instance parameter? For example, the solution size of a considered optimization problem or the maximal vertex degree of an instance graph. The problem that we want to consider as application for the balanced crown decomposition is the W separator problem, also called component order connectivity problem. Given is a graph and two parameters w and k, and we want to find the vertex subset of cardinality at most k, such that after removing them, that each connected component that remains has size less than w. Here, let me give you an example. For w and k equals to 3, we pick the 3 vertices here in the diagonal given in red as our solution. After removing them, we can see that each connected component has size at most 2, which is less than 3. We can also see the separator problem from the covering perspective. That is, we cover by these 3 red vertices each connected component of 3 vertices, so each connected component of w vertices here. For example, this subgraph contains 2 red vertices, this subgraph 1 red vertex, and this subgraph also 1 red vertex. Note that for w equals to 2 that we obtain the famous vertex cover problem, which shows that the w separator problem is a generalization of it. Now let's come back to our goal. We want to find the kernelization algorithm by the parameters k and w, such that we can bound the reduced instance by O of k times w. Let me give you a brief overview about the related work by this problem. So the problem is not fixed parameter tractable with the parameters k and w. That is, we can also not find a kernelization algorithms by the parameters k and w. The unweighted case is already investigated. Kumar and Luxtanov provides a 2 times k times w size kernel exponential in w. That is, when w is a constant, then the algorithm is a polynomial. Xiao provides a 9 times k times w size kernel in polynomial time, and we give a 3 times k times w size kernel for the unweighted case. We also extend this result to the weighted case, where we provide a 3 times k times w weight kernel, both in polynomial time. Lastly, I like to point out that probably 2 times k times w is best possible by the unique games conjecture. This is also a result what Kumar and Luxtanov achieve. Unfortunately, the algorithm is not polynomial if w is part of the input. Now let's come back to the w separator problem and our strategy how we want to reduce our instance. We try to find some vertices that we can pick as part of our solution, and now we need to justify that we really can pick them beforehand and afterwards reduce our instance by these vertices that we picked for our solution and all connected components that has size smaller than w. Here, for example, w is equals to 4. Let us change our perspective of this problem to the covering perspective. That is, we need to cover each connected component of 4 vertices. So if we pick a vertex now for our solution, then we want to map this to a subgraph which is connected and contains 4 vertices. What is here the idea? We know that we need to take one vertex for our solution of this subgraph here, because we need to cover it. And if the mapping is now disjoint, that is that we can map each vertex that we want to pick in our solution to a subgraph of W vertices, then we can justify that we can pick the head vertices probably in our solution. This is not enough, but this is exactly this kind of structure is exactly provided by a weighted crown decomposition. So first of all, each component of the crown weighs less than W. That is that we don't need really to pick a vertex here for our solution. On the other hand side, we can find through the mapping connected subgraphs such that each subgraph contains exactly one head vertex, each subgraph is connected, and each subgraph weighs at least W. That is that we need at least one vertex for this part of the graph. Finally, this is provable through the separation properties that we can pick the head vertices as part of our solution and allow to reduce our graph now by the head and crown vertices. So now let's say we have a balanced crown decomposition in hand. We allow to reduce our graph by the head and crown vertices by picking the head vertices as part of our solution, and then we end up with a connected vertex partition such that each part weighs between W and 3 times W minus 3. This is exactly here the body part. Because we, at first we used the lower bound that gives us the information that we need at least for each part at least one vertex in our solution, because we need to cover them, right? We need to cover each part by at least one vertex. That is, we can bound the cardinality of our partition by k. So the cardinality of the partition is at most k, which is the solution size. Afterwards, we can use the upper bound to bound the total weight of the graph, which results in a 3 times k times w minus 1 weight kernel. Let me summarize what happened here. We used the weighted crown decomposition part of our balanced crown decomposition to reduce our graph, and we used the balanced part of our balanced crown decomposition to bound the reduced instance. Now we want to summarize all of our results. For this purpose, let me introduce the W packing problem again, this time as a decision problem. So given is a vertex-weighted graph and we have two parameters W and K, and our goal is to find K connected disjoint subgraphs such that each of them weighs at least W. Here again the same example with K equals to 3. We also consider balanced partitioning problems. Given is here a vertex-weighted graph and a positive integer k, and our goal is to partition the vertices into k-connected parts of approximately equal weight. Here, for example, are 3 subgraphs. Each of them has similar weight here. Now, to achieve a balanced partition, there are two classical objectives, namely to maximize the lightest part, then our objective value would be 7, or to minimize the heaviest part, then our objective value would be 8. Now we summarize all of our results. We give some structural contributions. We provide the balanced crown decomposition, which is a structure characterization for graphs. We provide the balanced expansion, what we didn't see in this talk, but this is a structural characterization for bipartite graphs. We extend crown decompositions also for vertex-weighted graphs in polynomial time, and we improve running times, finding a Q expansion or a weighted expansion. Moreover, we improve the state-of-the-art kernelization algorithms for the W separator problem and the W packing problem, and we give first constant approximation algorithms for the W packing problem and for both variants of the balanced connected partition problem. To the end, I like to point out the factor of 3 that we can find in all of our results here. This is not by coincidence, this is exactly the ratio factor of 3 of the balanced crown decomposition that I mentioned in the middle of the talk. Thanks for watching the video.